All right, so we turn our attention here to the next section called solubility. Solubility is just an extension, really, of KEQ. There's a lot of similarities that you'll see here. But when we talk about solubility, we're talking about how compounds dissolve in water or in other, solvents. But solubility is generally talked about in terms of how it dissolves in water. So you've got certain solids at certain conditions would dissolve either really easily or not dissolve hardly at all. You have certain products in reactions, okay, that you would guess would be very soluble and not form a compound when the reaction's all over with. Or you would have products that you would guess, because of their solubility, and if their solubility is really low, you would guess that those products would probably come together to form a solid after your reaction. So solubility has a lot to do with predictions and basically how something will dissolve and how readily a product will come together and bond and be a solid in solution. So solubility. Some compounds readily, and this word is often used in chemistry, readily, it means kind of easily, and it happens spontaneously without a lot of obstruction. Okay, so some compounds readily dissolve in water, and some barely dissolve at all. This is what solubility is referring to, how well it dissolves. Table salt, for example, is a compound that dissolves easily in water, and that's something you've probably experienced. Also sugar, right? You put a little sugar or a little iced tea in your drink. Okay, that's mostly sugar. That dissolves pretty easily. You could also say that a lot of it, okay, a lot of it can dissolve in just a little bit of water. So if that's the case, if you say, you know what, I could take a lot of salt and put it in a glass of water, and I could just stir it up, and it'd look like it's gone. Well, it's not really gone, but it's dissolved, right? All the little particles have been enveloped by the water, like we talked about with surface area. We talked about, actually, I guess it was in physical science. We talked about kinetic molecular theory, right? And how these little particles get mixed up with the other particles. That's what dissolving really is. So if a lot of it can dissolve in just a little bit of water, this means that it is very soluble. Some other compounds do not dissolve easily. If they do not dissolve very easily in water, under, of course, similar conditions, then these compounds are said to be insoluble. So there's soluble and there's insoluble. Not unsoluble, not soluble, but insoluble is the word. So if these substances that are insoluble are in solution, they remain as a solid. And very little of that solid would actually sort of break off and be completely dissolved. A lot of it would remain as solid. So if you think about a rock, okay, a rock is fairly insoluble in water, right? If you put a rock in a glass of water and stir it up, that rock is going to pretty much stay as a rock, right? If there's any little dirt on it, that might dissolve into the water, make the water a little muddy or a little cloudy. There may be little pieces of the rock that would break off and get caught up in the solution, but for the most part, a rock is fairly insoluble. Does that make sense? Right? Soluble, insoluble. Now, solubility is the measure of how much something will dissolve. So if you were to measure how much of something dissolves, that's called solubility. So a high solubility, or a large solubility, and we'll say high, I don't like the word large really. A high solubility means that much of it dissolves. It's very soluble. That's the word that you would see, very soluble, which means that most of it dissolves, or more accurately, a large mass of the substance would dissolve. So in a given amount of water. Okay, so some things, high solubility means that it is very soluble, and a large mass of it would dissolve. If something has a low solubility, it's just the opposite. You would say it's fairly insoluble, and in order to get it to completely dissolve, you would only be able to put a very small amount of it in a large volume of water. Okay? Then it might dissolve. And of course, temperature and different things would affect that solubility, but we'll get into that a little bit later. Any questions so far? It's pretty straightforward, right? Okay. All right. So a dissociation equation, and of course the meaning of the word dissociation is to dissociate or to split apart. And if you see an equation like this, we've often called it a decomposition sort of reaction, right? But this is not a decomposition reaction because, well, I guess we would have called this a decomposition reaction. But really this is more a dissolving or a dissociation because you have Na, you have Cl, and really it's a pretty stark split, right? Just Na and Cl split, and they still remain Na and Cl. So it's a dissociation. And of course, the other thing you want to look for in a dissociation reaction, usually there's ions left in solution. When something dissociates, it's usually you find that there's positive and negative ions there. Well, if a decomposition reaction still would be more of a chemical reaction where you have substance A, okay, and it might break up into substance B plus C. So it wouldn't necessarily be just the ions, splitting apart. Okay, you might have, well, just off the top of my head, I mean, you might have, well, I don't know if I could think of a real good one here for you right now that would the difference, but I'll look at that later. But it's not necessarily a split where you get ions. It's, that's the big thing right there. If these compounds are not just simply the ions that make up, so like for example, this, if we had BC, and this split up into B plus and C minus, let's say, dissociation. But if we go back and look at, well, this is what we had before, right? A turning into B and C, that's more of a decomposition. It's decomposing into two separate things, not just the ions that originally make it up. You know what I mean? So that would be the difference there, I would say. Okay, good question though. All right, so here's an example of salt dissociating. Okay. The phase equilibrium equation represents the point at which the solid is dissolving and ions are reforming the solid at the same rate. So this is just like equilibrium, but this is the phase equilibrium. Okay? Now remember, phases are, solid, liquid, gas, but when we're talking about dissolving in solution, you're going to see solid, and then you're going to see aqueous ions here. You see? AQ. So phase equilibrium is like solid to aqueous ions, and back and forth. Aqueous means dissolved in water, literally. Yeah. Aqua, aqueous, basically means it's dissolved in water. So it wouldn't be appropriate to say solid and then Na plus liquid, because the ions are not really in liquid form. The ions are just simply kind of mixed up with the water, right? When we're talking about dissolving. So that's the difference there. But this is called a phase equilibrium, so you've got the double arrow there. And of course, if you think about a glass of water, right, and you've got some salt mixed up in there, and you stir it up real good, right, and you're stirring, and All of a sudden, there they go. They seem to be all gone. They're completely dissolved. But if you put more and more and more in, there comes a point where that glass of water will have some salt on the bottom, right? No matter how much you stir, okay, you're not going to dissolve that stuff on the bottom. You know, think of a real strong iced tea drink, right? If it's really strong, if you pour 2, 3, 4 teaspoons of iced tea mix into this glass of water, especially if it's cold, it's not going to dissolve very well. But you're going to have this all this sugar at the bottom, or in this case, all this salt at the bottom. What's happened there is the solubility has been reached, the maximum solubility has been reached, and you've added more mass than can be dissolved in that given volume of water. So if it all goes away, all right, there's still more that can be added that can be dissolved. But at this point, there are, NaCl that are splitting up into Na plus and Cl ions going into solution. But there are also Na ions and Cl ions that end up bumping into each other and precipitating out of solution, right, at the same time. So that's where that phase equilibrium. So becoming aqueous ions becoming solid. Solid becoming aqueous ions becoming solid. Okay? You get that? Just like equilibrium. Except it's not a chemical reaction forward and a chemical reaction backwards. It's just solid dissolving, ions forming solid. Okay? Slight difference there. Phase equilibrium. All right. So we did just finish studying equilibrium, and so that's where the similarity is. And so if you treat the dissolving as a phase equilibrium, we could write a phase equilibrium constant equation. Okay? So think about that for a second. We just did a KEQ, right? Where we have the concentration of the products on the top divided by the multiplication or the product of the concentration of the reactants on the bottom. So if we treated this like an equilibrium, this is the equation that we might write. And this is where the difference comes here. So I want to make this connection real clear. Products, Na plus, Cl minus. Reactants, NaCl solid. Now, does anyone see anything a little bit strange about this KEQ expression? Yes, normally the products are on the top, that's right, so that's the same. Is there anything in here that if we were doing KEQ, you might say, yes, very good. The solid. See, this concentration of solid, remember that doesn't really make sense. And when we did our ice charts, right, we only included the gases, okay? So if there was any solids, we did not include them in the ice charts because excuse me, concentration of a solid doesn't really make sense. You would have an amount of solid that would decrease, but not really the concentration, okay? Not really like the, the amount per volume, because a solid is just a solid. You can cut it in half, but you can't all of a sudden make it less concentrated. You know what I mean? If you cut something in half, a solid in half, and it's uniform throughout, it's sort of like the same concentration, whether you cut it in half or in a third or whatever. It's still the same stuff. The density would be the same, right? The composition would be the same still. So, the only issue here, and it's kind of right underneath here, the only issue is that this here, the concentration of a solid, is constant. And so, like I say here, from our ice charts, we didn't include solids. And so, this here becomes, the KEQ is a constant, and the concentration of the solid, or this number right here, would also be a constant. So the NaCl could change, the Na plus and the Cl minus, that concentration, those concentrations could change, but not this. So we end up having a different kind of constant right here. It's a KEQ times this number right here. And so that gives rise to the Ksp. Okay, did everyone have those notes there? I can move there? Okay. So the fact that we have another constant in the KEQ expression gives us a type of solubility constant. So the KEQ, when we're just talking about dissolving, okay, like a a reversible dissolving reaction, right? Dissociation reaction, we get a new kind of constant, and it's called the Ksp. So the Ksp is just based on the concentration of the ions that would be on the product side. We do not consider the solid part. So what we need to remember is the Keq, right, is for when all the concentrations can change, products and on the reactant side. The Ksp is for dissolving, and it includes sort of this, on the reactant side it's a solid. So this together makes the Ksp. What this tells us is the maximum product of the concentration of dissolved ions in solution that can exist before these ions recombine to form a solid. Okay, so that is pretty important, so I'll say that again. What the Ksp tells us, the solubility product constant, and I should maybe just expand on that. So that's called the, I did right there, sorry. It's right here. The solubility product constant, Ksp, solubility product constant, K. All right? So what this tells us is the maximum product. So if you have a certain concentration here and a certain concentration here, and if they multiply to the Ksp, this tells us how much of this and how much of this actually can be dissolved in solution. The maximum amount is the solubility product constant. So again, if we have a high solubility, that means that the Ksp will be relatively large. And why is that? Because the concentrations of the ions that would be in solution, there would be a lot of dissolved ions, right? High solubility, the solid would dissolve quite readily, there would be a lot of ions. And so the product of the concentrations would be very high. Make sense? A high Ksp means there's a lot of ions dissolved in solution. A low Ksp means that there's not very many ions dissolved in solution. That would yield a very small product constant. So another way of putting this is that it gives us an upper limit to the concentration of the ions that can exist before they bump into each other and form a solid compound again. So this is sort of the maximum concentration of ions that can exist before they form solid again. The upper limit for the concentration of ions that can exist in solution before they form solid compound again. So as I mentioned earlier with my little illustration, you add a teaspoon of salt to a large glass of water, you could dissolve it pretty easily, it's gone. You add a cup of salt into a glass of water, you may have a little trouble getting all of that to dissolve, right? You can kind of picture that. There'll be some on the bottom of the glass. And that means that you've exceeded its maximum solubility. That means that the number of, the concentration of ions, that solubility product, when you multiply them out, you're going to have more solid, more NaCl in solution than you can actually dissolve. So there's an upper limit. That's what the solubility product constant tells us. All right. So let's see how far we get here. You guys doing okay? I know this is a lot of just kind of notes. I'm trying to go at a reasonable pace here for you. Okay, so a substance that's highly soluble will have many ions, large Ksp. That's what we just said. A substance that is considered fairly insoluble would have a low Ksp for the same reason, because there's not a lot of ions that are able to be dissolved. So high solubility, highly soluble is large Ksp, fairly insoluble, low Ksp. Okay, so let's take a look at a bit of an example here. Don't write anything down here just yet. Let's just look at this together. Okay? So, in this example here, what does it say? At a certain temperature, and remember, solubility is dependent upon temperature. So, at a certain temperature, 0.02 molar of this particular ion, A+, and 0.3 molar of B- exists in solution. If this is the maximum amount of ions, or the maximum concentration of ions that can exist in solution without forming solid AB, okay, then we have a saturated solution. So a saturated solution, if something is completely saturated, like you guys are, you've probably heard the term, the market is completely saturated with this product, right? If you've heard that before, what does that mean? It's big, okay? It means that it's very popular. It means that, you know what, there's a lot of it out there, okay? If something is completely saturated, that means that there's as much kind of out there or in that kind of space that could possibly really exist. So if the market is completely saturated with iPhones, let's say, then that means that we really couldn't put any more iPhones out to market because no one would buy them, because the market is saturated right now. It's like no one wants to buy anymore because everybody's got one. That would be completely saturated, right? So if you think about that in a solution, think about we're adding more solid, we're stirring, it's still dissolving, but there comes a point where any more that you add wouldn't dissolve. That's the point where the solution is saturated. Okay, so if this is the maximum amount, if these are the maximum amounts that can be dissolved before it forms AB again, then the solution is saturated. Then we could also calculate the Ksp. So in a saturated solution, if we know these concentrations, we simply find the product, and this is the Ksp. Okay, that's the Ksp. And this is, of course, for the balanced equation, 1 to 1 to 1. So just like the KEQ, we're going to have to pay attention to the coefficients as well. A lot of it's the same. So this means that any product of concentrations of these ions that's greater than 0.006, so any product of concentrations of these ions greater than this number, that means we're going to get some solid AB in solution. So if the product is greater than this number, we are going to get solid. Anything that's less than this, so if we have a product of ions that's less than 0.006, we are not going to get any solid because more can still be dissolved. Okay? Another example. So let's say that we have, how many do we have in here? Well, 22 of us in here, okay? So in this class there's 22 of us in here. Now let's just say that this room could hold 30 people walking around without touching each other, without bumping into each other at all. 30. Okay? It would be, you know, maybe 15 boys and 15 girls, right? That's about the number. So this class only has 22 people in it, right? So if we all got up and moved around, we should be able to move around in this room without bumping into each other. We could add 8 more people, theoretically, into this room, and we still wouldn't bump into each other. But when we hit 31 people, right, the rating for this room, like the Ksp, is 30. So if we have more than 31 people in here, let's say we have 16 boys and 15 girls, then what that example would tell us would be that if we all moved around and there was 31 people, somebody would bump into somebody else. Okay? And if they bumped into each other, then they would have to, you know, they would kind of have to go to the side, and they would be like the solid. Okay? If we brought another whole class in here and there was 45 people in this room, wow. We would have a lot of pairs of people bumping into each other and going off to the side, right? How many people would we still be able to have walking around in here that wouldn't touch each other? So if we had 45 people in here, let's say we had 46 people in here, how many pairs do you think we would have on the side before we could kind of reach that phase equilibrium again? How many? Sorry? 8? You have eight couples on the side, maybe, or 8 pairs. Okay, so 16 people to get back down to that 30. That's a very good guess. Okay. Now, if you think about it, would we still have the same amount of space to move around, 30 people, if there were 16 groups kind of also in this room? Maybe not, right? So solubility, I mean, that's something to think about, right? Would we still be able to be bumping into each other? Well, what would happen is, if we had a phase equilibrium, the 30 people would be walking around, but probably one of them, they would bump into each other, right? Then what would happen if we were in equilibrium? One of those 30 people, or two of those 30 people would bump into each other. They would go off to the side, but what would have to happen if we were in equilibrium? If it was a phase equilibrium and we had two individual people bump into each other and then go off to the side of the room, what would have to happen for us to still be in equilibrium? Anybody? What's equilibrium again? Yes, exactly. Okay. Two of the pairs, two of the people would have to come back into the middle. So if there was a pair that paired off to the side, one pair would have to split up and come back into the middle. Okay? You guys get that? Are you picturing this? Okay? All right. Everyone just sleepy, or are you just really not getting it, or are you just shy? You're all shy. Okay. I'm glad you all said you were shy. I hope that makes sense. But anyway. Okay, so there's a little example that you can think about. You can also, with this Ksp, you can also calculate individual concentrations of ions, and I think this is where we might stop after these sort of notes here. So this is the last section that we'll probably do today. You can calculate individual concentrations of ions if you're given the Ksp. All right, so look at this. If you're given a Ksp, and you've got, this right here, but you're given this, you can solve for these right here. And this is how we do this. So we want to write these notes out here. Okay, so what are we doing again? Your title would be to calculate individual concentrations of ions given the Ksp. This is how you would do it. These are the steps. Number 1, write the equilibrium equation, or in this case, the solubility, right, expression. Okay, so we talk about a phase equilibrium, right? What you want to do then is use a single variable. So again, we're solving for these things right here. So we want to use a single variable to represent the expressions for each ion. And an example is given below here, but let's get through the steps. Step 3, write the Ksp expression. And in that expression, you want to include the values for the Ksp, a value for the Ksp, and the variables for the unknown ions. Solve for the variable. So you're going to have to do a little bit of math here. And then use the variable to determine the concentrations. So this is very, very similar to the ice charts, right? After you filled in the ice chart, you had to do, this is exactly what you had to do. Write the equilibrium, fill your values in, solve for the variable, determine what that variable is actually representing, and give your answer, right? So it's very much the same as the ice charts. Okay. So here's an example. Here's an example that we'll go through together. And again, you guys are in grade 12. This math should be really simple for you. If you can do the math and the ice charts, you'll be able to do this one pretty quick. All right. So this example says, given that the Ksp for barium carbonate is 2.6 times 10 to the negative 9. Now, would this be a very large Ksp or a pretty small Ksp, do you think? Yeah, it is pretty small. The -9, okay. We're gonna take a look in your textbook here very shortly at KSPs, and if they're in the back of your textbook. But you'll see there's lots of even smaller ones than this, okay. And the compounds that are fairly insoluble, do they have a high KSP or a low KSP? Insoluble means they have not very many ions, so that product is going to be small. Yes. So we are expecting not a whole lot of this to dissolve, right? But there will be some. So the question is, find the concentrations of each ion in the saturated solution. So the maximum amount of each product, each ion that we could have. All right, so write the equilibrium equation. So we have solid, you can write solid in there if you want, solid barium carbonate, reversible reaction here, entering in phase equilibrium with aqueous barium and aqueous carbonate ion. So there's your KSP, that's step 1. Now because this is a 1:1:1 ratio, remember what that ratio means, it's moles, okay? Molar ratio. So if I have 1 mole of barium carbonate dissolving, I should have 1 mole of barium ion. I think there's actually something didn't get, just noticing here. This should be, I'll have to check my notes. It should be 2 plus and 2 minus here. Just notice that. Barium, you have barium ion and carbonate ion. So you have 1:1:1. So 1 mole of this produces 1 mole barium and 1 mole carbonate. Oh yeah, it's down here. I guess I just missed that typo. So if this is happening, it's a 1:1:1 ratio. So if you let barium be X, then carbonate is going to be X as well. Remember like the ice charts, right? If you have X, a change, so this is forming X amount. If it's a 1:1 ratio here for the products, it's X and X. So that's why they're both going to be X. An unknown amount of the concentration of the final ion. So again, just like the KEQ, it's just like KEQ. You start with a reactant and you let it, decompose, or you let it dissociate until you get to an equilibrium. And so we're trying to find out what point that is, and it's based on the value of the KSP. All right, so from your Ksp expression down here then, you would basically fill in all your values. Here's your Ksp equals x times x, or x squared. Take the square root of both sides, and you have this value for x right here. And what does that value give us? Well, remember we set x to be the concentration of each of the ions at phase equilibrium. So therefore, your answer here is the concentration of barium and carbonate ions are both 5.09 times 10 to the negative 5 molar. So what this also means, if you're understanding KSP, is that the solubility of barium carbonate at this temperature is 5.09 times 10 to the negative 5 molar. So how much of barium carbonate could dissolve? Remember the 1:1 ratio? Okay. Back here, 1 mole of this produces 1 mole of this and 1 mole of this. So if the concentrations of Ba and CO2 are both this number, that's exactly how much barium carbonate could dissolve. So if we're talking about an amount, and the solubility is how much can dissolve, right? That's the concentration of barium carbonate that could dissolve, because it's a 1:1:1 ratio. So this number, 5.09 times 10 to the negative 5 molar of each ion, came from 5.09 times 10 to the negative 5 molar of the original barium carbonate. 1:1:1 ratio. of moles. Moles per liter. Okay, so I know that's a big lesson, that's a lot to absorb. We'll do some more examples, but there's sort of the instruction on solubility, Ksp, how to find Ksp, how to solve for unknown amounts of the ion as well. Okay, so we'll just do some examples next. Okay, so in this example that we're going to do here, it says, what is the ion concentration in a saturated solution of copper 2 iodate? So the ion concentration of all of the ions, we can say ion concentrations, I guess, of all ions in the solution of copper 2 iodate. Okay. Now, this is the type of question that you'll be given. There's a few things that you're going to have to be able to do on your own, which is, if you don't know the formula for copper 2 iodate, you're going to have to kind of reach back into the data banks there and figure that out. Okay, you can look it up in the textbook. Look up what iodate is, what that ion looks like, what charge it is. Remember page, I think it's 169 in your textbook. Yes. Page 169. Go there, and you should see that has a chart of common ions. Okay, that's a chart that we used heavily in chemistry classes before this. So anyways, so copper 2 means that you have Cu2+, right? That's what copper 2 is. All right, what's the iodate ion? IO3, and what's the charge on that? Should be -1, that's right. Okay, so identify these ions, and of course this is copper 2 iodate is a solid, right? So what's the solubility? What's the ion concentration at the saturated solution? So we have copper iodate. Now how do I write a proper formula for copper iodate given these charges here? Remember how to write the formula? The charges have to what? They have to balance out. You guys remember that? Okay. And so I have 2 plus here. I only have 1 minus here. So I need 2 of these, right? And in the formula, you do that by, if it's a polyatomic ion, you put the brackets there and you put a 2 there. Right? This copper 2 does not mean that you have to have a 2 there. Okay? Just make sure you remember that. So copper 2 iodate, and we're looking at what happens when we're at phase equilibrium with our ions. So Cu2 plus IO3 minus. Is this equation good? Anything we have to do here? We want to work with a balanced equation, right? So what do we need to do? Yeah, that's right. Right here, we need to have a 2. Because over here, there's 2 iodate ions in this compound. So we need to have 2 iodate ions represented over there. Very good. So if we're looking at molar ratios, we have a 1 to 1 to 2 ratio. You want to see that? Okay. So in order to solve this problem, what we're going to do is we're going to write our Ksp expression. So Ksp equals concentration of Cu2 plus times the concentration of IO3 minus. Now, just like the Keq, what did we do with the Keq when we wrote the Keq expression? What did we do with these coefficients? Yes, we made them into exponents. So that's the same thing you're going to do with the Ksp. So because there's a 2 here, it's going to have to be a 2 here. Now, this next part is a bit tricky. This is where students in the past have kind of done the, what? Okay, like, what's going on? What? How can we do that? I need to explain something, okay? So if we have X number of moles here of copper iodate dissolving, we get X number of moles of copper 2 plus, and we get 2x moles of this forming. So it's a 1 to 2 ratio. So if I am going to let something be X over here, I'm probably going to let Cu, the concentration of Cu, be X. So how do I represent the concentration of IO3 then? It would be 2x. Okay. Now, what? Is that strange? Nope. That's not very strange. Let's see if I can just carefully insert some space here. Nope, that didn't work. All right. I'll try the lasso effect here. Lasso. Oh, beauty. Okay. So this is x, and this is going to be 2x because it's a 1 to 1 to 2 ratio. That means that in the Ksp expression, I have x here, and I have what inside here? 2x squared. So yes, you have to double the x, and you have to square it, both. Okay? That's not strange. That's not weird. Okay? Don't think that that's weird. Yes, you double it, and you square it for the expression. Okay? Because that's how it works. Yes, of course we're gonna simplify that now. So the Ksp is given as, let's just complete this here, 7.41 times 10 to the negative 8 equals x times 4x squared, right? Which is actually 7.41 times 10 to the negative 8. That's going to be 4x cubed. Divide by 4. Take the cube root, right? Then we're going to get x all by itself here. So your assignment's page 604, 1 to 6. Some more practice on this calculating Ksp and unknown concentrations.